All right, let's look at some Lewis dot diagrams. You should remember how to draw Lewis dot diagrams, Lewis dot structures, electron dot diagrams, whatever you want to call them, for single elements. So here's a sampling. You can see what it looks like when there is one valence electron, when there are two valence electrons, 3, and so on, all the way till down here is 8. Remembering helium is the exception. Its 2 does not look like this. Its 2 looks like this because it's stable. Why? Electrons that are single will bond. Electrons that are paired will not bond. So looking for single electrons, you can find out how many bonds something will form. Okay, so 8 dots maximum of 2 dots on each side. So remember, we're imagining the symbol of the element inside a box. We could put 2, and notice they go vertically on this side and they go horizontally on this side. Okay, the dots should be filled in, not open circles. All right, so now let's look at ions. What do? So a chlorine atom has 7 valence electrons, so it looks like this. When it becomes an ion, it gains 1 electron. Now, when it's an ion, we put it inside brackets. We added that extra electron, so now it has 8, but we indicate that it has a charge, so negative. So how many electrons does chlorine have now? Total of 18. It had 7 valence, but it had 17 total electrons. Notice this doesn't say valence. This just says electrons. And this is the same as what noble gas? Well, you go to your periodic table, you open up, and you see what noble gas has 18. And you look, and it's down here. That's a little blurry looking that way. It is argon. Okay, let's look at another example. So here we have sodium atom. It has 1 valence electron, so this is its Lewis dot structure. It loses 1 electron. So when I draw the Lewis dot for the ion, I put the bracket still. I put the charge, which is +1. But notice I don't have any dots because it lost this 1. Okay? So how many total electrons does it have? Well, when you look on the periodic table, sodium starts with 11, but it lost 1, so it has 10. And that's the same as what noble gas. So you look, what noble gas has 10 electrons? That would be neon. Okay? So draw the Lewis dot structure for an atom of magnesium in the ground state. Symbol, look it up on the periodic table, valence electrons, it has 2. 1, 2. Should look like that, right? That's what I drew. Draw the Lewis dot structure for a magnesium ion. So here's the symbol. When I look at the periodic table, it says the oxidation state of magnesium is +2. So it lost 2 electrons. It does not have any left. It should have no dots and look like this, like that. Draw the Lewis dot structure for an atom of oxygen. Symbol, 6 valence electrons, 1, 2, 3, 4, 5, 6. There we go. Now notice it doesn't matter which side you start on, you should end up with 2 pairs next to each other and 2 unpaired next to each other. Draw the Lewis dot structure for an oxide ion. So oxygen started with 6. Check the periodic table. It has an oxidation state of 2 negative. So I need brackets for an ion. And then how many dots? Well, it started with 6 and gained 2. Right? So looks like this. So in case you didn't notice, if it's a positive ion, no dots. If it's a negative ion, 8 dots. Okay? When we draw the Lewis dot structure for ionic compounds, it's easy. We just take the Lewis dot structure for the metal cation and the Lewis dot structure for the nonmetal anion and just write them next to each other. So now let's look at covalent bond types. So we can have a bond where 2 electrons are shared. How do you know how many electrons are going to be shared? Look for unpaired electrons. So if I'm bonding H with Cl, Cl has 7, 1 unpaired. H has 1, 1 unpaired. So I'll be able to pair those two electrons and make a bond. Why are they sharing anyway? Because it's two nonmetals, so it's covalent. So I end up with two electrons shared between them. That's called a single bond, okay? Here's another example, two electrons shared, single bond. If you have four electrons shared, that's two pairs of electrons, it's called a double bond. Because when we look here, when we're bonding these two atoms, I have unpaired, I have unpaired. So this one has two unpaired. This one also has two unpaired. So since there's nothing else bonded to it, the only option is to make two pairs. When I have 6 electrons shared, that's 3 pairs. That's called a triple bond. So that's I'm bonding these two atoms. This one has 1, 2, 3 unpaired. This one has 1, 2, 3 unpaired. They both have 3 unpaired, and I'm not bonding it to anything else. So I end up with a triple bond. 6 electrons, but 3 pairs. Okay, so again, here's how you can tell. So here's carbon, and it has 1, 2, 3, 4 unpaired electrons. Oxygen has 2, this oxygen has 2. So on each side of carbon right here, I'm going to get a double bond on each side. Here you can see why I have triple bonds. 3 unpaired here, 3 unpaired here equals a triple bond. Again, single bond, 2 electrons, 1 pair. Double bond, 2 pairs, 4 electrons. Triple bond, 6 electrons, 3 pairs. Now, how do we draw the Lewis dot structures? Okay, so we're going to be using model kits. Okay, so you're going to have a container like this with bonds. You're going to take the lid off so that you can access the bonds. Okay, and then you have this kit. You're going to remove the rubber band, open it up, and you're going to see the other part of the kit. Okay, and then on the lid is a key. Okay, so we are going to use that as well. So that's what we're going to need in order to build and see shapes. All right, so we are going to be working with Cl2. So let's look at the periodic table. Cl is right here. Look at its electron configuration. The last number is 7. So chlorine has 7 valence electrons. So watch, 1, 2, 3, 4, 5, 6, 7. But I have 2 of them. 1, 2, 3, 4, 5, 6, 7. So that gives me a total of 14 electrons. So however I draw it, I cannot have more than 14, okay? But remember that every atom wants to have 8, but it doesn't have 8 right now, it has 7. Chlorine is a nonmetal. Chlorine is a nonmetal. So when a nonmetal bonds to a nonmetal, we get a covalent bond. And since it's 2 atoms of the same element, it is specifically nonpolar covalent. How could I do it math-wise to find that out? Well, I would go to table S and I would look up chlorine, and has an electronegativity of 3.2. So I would do 3.2 minus 3.2 equals 0. And that is, again, nonpolar covalent. So now how do I draw the Lewis dot structure of Cl2? Well, all the electrons that are paired up already are not going to bond. Okay? So when I only have 2 elements, it's actually easy. You're going to write the 2 elements next to each other, their symbols, leave a little bit of space between them. Look for how many electrons are not paired. Well, there's only 2. I need 2 electrons to make a bond. So I put those 2 electrons between them. Now they're shared. Okay? And then what I do is around this Cl, see I had 3 pairs already, and around this Cl I had 3 pairs already. So now when I count the electrons around this chlorine, I have 2, 4, 6, 8. When I count the electrons around this chlorine, I have 2, 4, 6, 8. The ones in the middle count for both. Okay? Remember I said we couldn't have more than 14 electrons? So let's count. 2, 4, 6, 8. I already counted those. 10, 12, 14. So there, this is what it looks like. How else you can draw when you have the 2 electrons in between, you can represent the 2 electrons with a line. Okay? And then I'm still going to add those unbonded, the paired already electrons like that. So this is correct and this is correct. All right? Now let's see how to build it. So we have to look at its shape. All right? So chlorine here is green. All right? So I'm going to go to my model kit and I have 2 CLs. So I'm going to get 2 greens. All right? And then I'm going to get a bond. It doesn't matter which one I use. And what I'm going to do is put this here, put this here. That's it. Notice on the green there's no additional holes, so that automatically tells me this is right. So this is what Cl2 looks like as a shape. Fun fact, when it's 2 elements, it's always going to be the same shape. We call this shape linear. Okay? Now, a linear shape, okay, if this molecule right here, this is the molecule, it could be polar or nonpolar. What I have to do is figure that out. I already said this bond was nonpolar covalent, so that's the end of the story. When the bond is nonpolar, the molecule is nonpolar. So that's it. So this is a linear nonpolar molecule. This is a nonpolar covalent bond. Okay? All right, we're going to do another one. Are you ready? HBr. Okay. So I need H has 1 valence electron. Br has 7. 1, 2, 3, 4, 5, 6, 7. At this point, you should know that I'm looking up those valence electrons on the periodic table. Okay, I'm going to stop showing you that part. You should know it at this point. All right, so let's look. Bromine has these paired already. They will not bond. Has 1 electron right here that wants to bond and 1 electron right here that wants to bond. Kind of a perfect matchup. So let's check what kind of bond it is. Hydrogen's electronegativity is 2.2 and bromine's electronegativity is 3.0. Okay? So that difference is 0.8. That is a polar covalent bond. Remember, when it gets above 1.7 roughly, it's going to be considered ionic. But the scale looks like this. So 0, that is always 100% without a shadow of a doubt nonpolar covalent. Okay. Then we have 0.4. And between 0.4 and 1.7, we usually consider that to be polar covalent. And above 1.7, it's ionic. But in reality, if it's not 0, like if it's not nonpolar covalent at 0, then it's a little bit polar covalent, it's a little bit ionic. When the numbers are low like this, low like this, low like this, it's more polar covalent than ionic. And when we get bigger numbers, it's ionic. But it's not an absolute. So that's why we only grade it. Like if something is more polar, it has a bigger difference. Less polar, smaller difference. Okay? And then usually we can tell ionic because it's metal and non-metal. Okay? And then polar covalent and non-polar covalent will be 2 non-metals. Okay? So anyway, so we have a polar covalent bond. I only have 2 elements, so I'm going to draw them next to each other. Okay? And then I'm going to put those unpaired electrons between them. Now they want to share them. I'm going to add the paired electrons that don't bond around bromine. I don't add anything extra around hydrogen. I can replace those 2 electrons with a line in between. Okay, so it can look like this, right? Now remember, this was a polar covalent bond, right? So let's build it and look at the shape. So bromine is this deep blue, and hydrogen is white. So I'm going to go to my model kit, and I need a deep blue and a white. Wait, it's not this one. I don't think this one has any deep blues, because this is definitely not. Well, we'll just use green because it follows the same pattern, okay? So a hydrogen and a bromine. Okay, so like this. Notice they don't have any other. Now, why did I use that? Because remember, this was Cl2 and that's a halogen. Bromine's also a halogen, so it follows the same rule. So I look at this. Again, remember, anytime it's just 2 atoms that are bonded, our shape is going to be linear. Now I want to talk about the molecule. Is the molecule polar or is the molecule nonpolar? Well, I look at the bond type. The bond type was polar, and there's only one bond. So the molecule is also polar. So I have a polar molecule with a polar bond, okay? Okay, let me show you just one more thing I forgot to show you. So H, we started with 1 electron. Bromine, we started with 7. So we started with 8 total electrons. In our final picture, we cannot have more than 8. So 2, 4, 6, 8. Perfect. Look around bromine. 2, 4, 6, 8. Look around hydrogen. 2. That is all hydrogen is supposed to have. That's perfect. If we were counting from this one, 2, 4, 6, the line counts as 2, 8. Okay? We are on to N2. Sloppy. All right, so we have an N and an N. You look it up on the periodic table. Each nitrogen has 5 valence electrons. So it looks like this, right? So that gives me 10 total electrons, 5 plus 5. So however I draw my answer at the end, I can't have more than 10. So this is a paired set. They're not going to bond. So each nitrogen has 3 unpaired electrons. So let's draw the nitrogens next to each other. Okay. And I need to put all of the unpaired, but I'm going to pair them up. So I'm going to take one from this one from this one, put them next to each other. So I use that one, right? Take one from this one from this one, put them next to each other. I'm putting all of the shared ones that I'm sharing now in between. One from this one from this one. Then each one has a paired already set that I have to add. You could put it on the top. Standard, we're going to put it over here, but in reality, it doesn't matter as long as you put it on the correct atom. So first, let's check electrons, because this looks kind of wrong. 2, 4, 6, 8, 10. Okay. Now I have to check each atom. Does each one have 8 around it? Well, let's check this nitrogen. 2, 4, 6, 8. Let's check this nitrogen. 2, 4, 6, 8. So do you see, by making this in between, I literally made each nitrogen have an octet. So what do we call this? Well, remember, each pair I can draw as a line. So I'm going to draw 3 lines like that. So this is actually a triple bond, okay, between these 2 nitrogens. So 6 electrons, 3 pairs, a triple bond. So what kind of bond is it? Well, if I look up the electronegativity for nitrogen on the reference table, it's 3.0. So you do 3.0 minus 3.0, it's 0. So this is a nonpolar covalent bond. Okay, so let's see what the molecule looks like. All right, so we got to get nitrogen. So for nitrogen, we need blue. Okay, so we're going to use this one right here. Okay, and this one. All right, and then I need some bonds. All right, so we're going to use these longer ones because you see they're going to have a little bit more stretch. So I'm going to find how many bonds did we have? 3. So I'm going to find them like this. Okay. And what I'm going to do is put this in here like this, and then here. All right. Then I'm going to find another one like this right here, and then see how these bend around. Okay. Then I'm going to connect it here. A little tight on the squeeze. Okay, like this. Then I'm going to take this one and I'm going to get all the way around. Whew, like that. Look at that. Okay. Now when I talk about the shape, remember there's only 2 atoms, right? So the shape is automatically linear. All right. Now the molecule can be polar or nonpolar. Well, since the bond was nonpolar, the molecule is nonpolar. End of story. So I have a linear molecule that is nonpolar, a nonpolar molecule that has 3 nonpolar bonds. Okay? Go back to this one. This was a polar molecule with a polar bond. This was a nonpolar molecule with a nonpolar bond. All right? All right, next one, CH3Cl. So I have a C, I have an H, another H, another H, and a Cl. Okay, 4 valence, 3 total valence, and then I have 7 valence. All right, so let's see how many electrons I have total. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I have 14 total electrons that I have to work with and make a bond. So carbon is always going to go in the center. Also think about it this way, the one that you have that has the most bonds that it can make, you're going to start with that one. Okay, so I have, let's just do this one first. So I'm going to take this electron and put it here, and take one of these hydrogens and take this electron and put it here between them, and then put the atom. So I use that one. Okay, now I'm going to take this one. I'm going to put the electron that came from carbon right there, and then I'm going to take this electron from hydrogen and then write the H on that side. I use that one. Do the same thing over here. One from carbon, one from hydrogen, put the hydrogen. Okay, now I still have this one from carbon. So what am I going to put there? Oh, well, look, chlorine has an open one. So let's put the chlorine right there. So I put the dot, then I put the chlorine. But now I need to add these paired ones that were already around chlorine, like this. Okay, so let's check electron totals. I should have 14. 2, 4, 6, 8, 10, 12, 14. Perfect. I should check around each atom. Hydrogens need 2. 2. Hydrogens need 2. Hydrogens need 2. Every other atom is going to need 8. So check the carbon. 2, 4, 6, 8. Beautiful. Check the chlorine. 2, 4, 6, 8. Beautiful. So this is done. Okay. Now I have two types of bonds. Okay. So I have a CH bond and a CCl bond. So I have a CH and I have a CCl bond. Right. So let's check the carbon to hydrogen. Okay. So carbon is 2.6, hydrogen is 2.2. So 2.6 minus 2.2, 0.4. So that is really a non-polar covalent bond. And C is still 2.6. And what is Cl? 3.2. So 3.2 minus 2.6, 0.6. So that really sides on the polar covalent. Okay, so it's got 3. So this is non-polar covalent, non-polar covalent, non-polar covalent, and this one is polar covalent. I could write this one like this with the extra dots around chlorine. Okay, so I've got non-polar covalent, non-polar covalent, non-polar covalent, and then polar covalent. So let's see how this plays out when I make the shape. Okay, so I need a carbon, 3 hydrogens, and a chlorine. I already know chlorine's green, hydrogen is white, so what is carbon? Carbon is black. Okay, so I need to get carbon, 3 hydrogens, and a chlorine. Okay. So let's get bonds. Did I need any double bonds? Nope. So I am just going to get 4 of the little ones. Okay. And I'm going to put a bond from hydrogen to carbon. Put a bond from hydrogen to carbon, hydrogen to carbon. It doesn't really matter which side goes where. Then the last one, so one of them is just going to go like this. Okay, so now what? Okay, so look at this molecule. This is a little bit lopsided, right? So this molecule has non-polar bond, non-polar, non-polar, and then a polar bond. This shape is called tetrahedral. Okay, so that's the name of that shape. And this molecule can either be polar or non-polar. So when we're looking for polar versus non-polar, okay, non-polar could be all non-polar bonds. All right, it could have symmetry and equal charge distribution. Polar has to have at least one polar bond. We have one right here. Okay, it has no symmetry, and the charge distribution is unequal. Okay, so this does not have symmetry, right? Because look, this green one right here. If this green one wasn't here, it might be a different story, but it is. So this one right here makes this not have symmetry. So then I know my molecule is polar. But what do I mean by charge distribution? Well, when it's non-polar bond like this one, the electrons aren't being pulled strongly one way or the other, so the charge is distributed equally. But for this bond, chlorine has a higher electronegativity, so it's pulling the electrons closer here, so the charge distribution ends up being unequal. So this molecule is polar, okay? This is a polar molecule. Now, if it was this, look at that symmetry, so that would be polar, okay? That would be nonpolar. I mean, this would be a nonpolar molecule. It wouldn't be polar anymore. But let's keep our example. So this was a polar molecule because it did not have symmetry. This is a nonpolar molecule because it had all nonpolar bonds. It has symmetry. It has equal charge distribution. This molecule was nonpolar because it had a nonpolar bond and also equal charge distribution and symmetry. This one was a polar molecule because it had a polar bond. It has no symmetry and it has unequal charge distribution. Okay, so that's everything that we covered. All right, CO2 is next. So carbon, oxygen, oxygen. Okay, how many total electrons? 6, 6, 12, 13, 14, 15, 16. 16 electrons. How do we bond it? Well, okay, so we put carbon here, right? And then if we can split things evenly, we're going to put one on each side because you see I could put it anywhere. So we're going to put one on each side. This is one you just kind of have to remember for carbon dioxide. Okay, but when I build it with the model, you'll see why. Okay, so what happens, I'm going to take this one from carbon, and I'm going to take this one from oxygen. But this one is another one, so I'm going to take this one and this one. Okay, so that accounted for all those unpaired, but this oxygen has two paired like this. I'm going to repeat the same thing on this side. Take this one from carbon, this one from oxygen, this one from carbon, this one from oxygen. And then the oxygen has the two pairs like this. Looks like this. Let's check. 16, 2, 4, 6, 8, 10, 12, 14, 16. Let's check around. Each one needs 8. 2, 4, 6, 8. This carbon, 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. Perfect. I can draw it like this. This is a double bond. That's two pairs of electrons shared. Okay? So this. What kind of bond is this between carbon and oxygen? Well, carbon is 2.6. Oxygen is what? 3.4. 0.8. So that is a polar covalent bond, right? So polar covalent bond, polar bond. Okay, so let's see about the shape of the molecule. So carbon is black, oxygen, what we haven't used yet, is red. Now I need double bonds, so I need to get the big ones because I have to allow them to bend. Okay, so I need the bigger ones. And I'm trying not to take apart the ones I had already because I want to show everything that I have so far. Okay, perfect. I have enough. Okay. So I'm going to take a carbon and connect it to an oxygen. And I'm going to take the same oxygen and connect it to the carbon. And I dropped a bond. So, okay, there we go. And then on the other side, I'm going to take a carbon, connect it to oxygen. I'm going to take the oxygen and connect it to the carbon. So look at that. That shape is linear. Look at that. Okay, so that means I have a polar covalent bonds pulling this way because oxygen had the greater electronegativity, right? So polar covalent pulling this way and polar covalent pulling this way. So this is symmetry. So even though all of these bonds are polar covalent, the molecule is non-polar because there's symmetry and equal charge distribution. I have the same amount pulling this way because these are both oxygen. They're both pulling the same. So this is a non-polar molecule with polar covalent bonds. This is a polar molecule because it doesn't have symmetry. Non-polar molecule. Polar molecule. Non-polar molecule. Phew. All right. All right, let's do O2. So O looks like this. 6 and 6, it's 12 electrons. How do I draw them? Well, it's only 2, so I put them next to each other. How many that don't have bonds, that aren't paired already? 2 from this one and 2 from this one. So I put all 4 in the middle. Add the paired ones like this. Check that I have 12. 2, 4, 6, 8, 10, 12. How many around this oxygen? 2, 4, 6, 8. How many around this oxygen? 2, 4, 6, 8. I could draw it like this. Okay. This is a non-polar bond, okay, because it's 2 oxygen. When I subtract them, I get 0, which means automatically, since it's a non-polar covalent bond, the molecule is also non-polar automatically. And since it's only 2, the shape is linear, but let's see it. But I need a double bond, right? So I need the long ones, so they'll stretch. So oxygen to oxygen. Let's do it like this. All right, and then oxygen to, sometimes a little, there we go, oxygen to oxygen. So this is a nonpolar molecule with nonpolar bonds, linear shape. So linear, 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 tetrahedral, linear. Okay. All right. Okay, so here we go. Here's this one. I already prepped this, NH3. Okay, so here's N. I have a single electron right here. I'm going to use one of the ones from hydrogen. Single electron here, use one from hydrogen. Oops, I forgot to write the H. And a single electron here, use one from hydrogen. Then I have a pair right there. I should have 8 total electrons. 2, 4, 6, 8. Well, obviously, then I just counted around nitrogen, right? And hydrogens only need 2. Each one has 2. So I could draw it like this. All right. So what about the bond? Well, between nitrogen and hydrogen. Nitrogen's electronegativity is 3.0. Hydrogen is 2.2. So each one of those bonds is polar covalent. All right. So let's see the shape. So nitrogen, we did that before, is blue. Okay. And hydrogens are white. I don't have any double bonds or anything, so I can just use whichever bonds I want. Just use 3 of the same because these are the same elements bonded to each other, right? So I'm just going to use the same. So I'm going to connect it like this, and like this, and like this. Okay, so there. This is called trigonal pyramidal, and this is polar because you see there's not symmetry here. There's not equal charge distribution because the nitrogen is pulling harder, so it's pulling here, it's pulling here, it's pulling here, but it's not pulling up on this plane, right? It's like missing it up here. Why? Because this extra pair of electrons, they're up here. So this is a polar molecule. When we have this shape, it's always polar. Okay? Okay, last one. So I'm going to start with O because that needs the most bonds. I'm just going to add the paired ones already. So I have an unpaired and unpaired. What can I plug in? A hydrogen and a hydrogen. So like that. 8 total electrons, 2, 4, 6, 8. Just counted around oxygen. Each hydrogen has 2. I can draw it like this. It's important to start with the Lewis dot structure so you end up with it correct. Okay, so what kind of bond is this between O and H? Well, O, if you remember, is what? 3.4 minus hydrogen, 2.2, 1.2. So those are polar covalent bonds. So let's build it. We need 1 oxygen and 2 hydrogen, and we just need 2 bonds. So just get 2 of the same, and we'll bond oxygen with hydrogen and oxygen with hydrogen. Looks like this. This shape is called bent. And this molecule is going to be polar. This is not symmetry, okay? And because the electrons are pulled closer this way and closer this way is not symmetry. There's nothing up here, okay? So this is going to be a bent shape. There's only one more that I'm just going to show you real quick, and this is if we had BH3. So I'll write it down in a second. But just because this is one more shape that we could have, okay? BH3, and that is going to be trigonal planar. So it's going to be nice and flat, okay? So unlike NH3, which was trigonal pyramidal, this is going to be trigonal planar, nice and flat, so that has symmetry. So that would be BH3, and that is trigonal planar. Okay, that's it. So trigonal planar, symmetry. Trigonal pyramidal, no symmetry. Bent, no symmetry. Tetrahedral could have symmetry, but this one does not, so that's polar. The rest of these we built are all linear. Could be polar or nonpolar, but this was the only polar one that we built. The rest were all non-polar. There you go.